In this video, we'll take a look at how to do long-term spectrum monitoring with a real-time spectrum analyzer. We're going to use some of the standard features in the DPX display. A quick reminder, the DPX display that we're looking at here is composed of tens of thousands of spectrum measurements per second overlaid on top of each other, and the amount of overlap or density indicated by the color grading. In this case, a red color grading means that we have a lot of overlap, so that's most of the time we're seeing effectively noise floor here. We work our way down through the reds, the yellows, into the greens, the light blues, and the dark blues for the less frequently occurring things. And we can see, in this case, we're looking at a couple of wireless LAN beacon bursts here, a couple of Zigbee bursts both here and here, and this hunting transceiver signal is looking for my wireless headset. The yellow trace is just a max hold that's shown with each DPX spectrum update. Now, a standard feature within DPX is to build what's called an O-gram, or a waterfall display. And down here in the bottom left corner, you can select the DPXogram, or in my case, I'm going to choose Split. And that will show both the DPXogram and the DPX spectrum display. Now you can see the DPXogram is really nothing more than effectively a strip chart of spectral activity over time. And each row of pixels in the O-gram is really just a spectrum trace. And the color is indicating the amplitude. In fact, a good way to look at this, if we right-click and add a marker, if I move that marker through in time, you see the red trace down at the bottom is that spectrum trace being yanked out of that O-gram. The DPXogram can keep track of up to 60,000 spectrums. So depending on what we set our time scale to, we can have this long-term spectrum monitoring occur over a very long period of time. The time scale here right now says 250 milliseconds, refers to the amount of time between the tick marks here on the left-hand edge of the DPXogram, so a quarter of a second. We can increase or decrease this as needed. If we increase the amount of time, so in this case it's now 2.5 seconds, you can see it takes 2.5 seconds to fill the 50 spectrums that occur between each of the tick marks. Now you'll also notice, if I stop this real quick, we can see now that the DPXogram trace, the red trace where the marker is, looks like it composes of a couple of these hops. And that's because at this setting, the amount of time that each of these spectrum slices is using is long enough to see 3 of those hops happening. Because the trace processing that's happening to build the spectrum traces into the O-gram is really a max hold. In fact, if we go to settings, to the traces, and take a look at the DPXogram, it's using a positive peak trace. So we're taking those tens of thousands of spectrums per second that are occurring, and then taking a look, in this case, under time and frequency scale, I've got a 50 millisecond resolution from one tick mark to the next, right? That's the 2.5 seconds divided by 50. So within that 50 millisecond period, 3 of those hops are occurring. So that's why the DPXogram trace has got 3 hops in it. If we run this again and speed things up here again and bring our time per division down, so now I've got just 2 milliseconds per spectrum slice. And if we stop this here again and move my marker through this, we can see that each of the hops is only occurring effectively in 1 of the spectrum traces. Now, because the DPXogram traces are built up using that positive peak trace from thousands of spectrum measurements a second, there's really nothing missed in the spectral recording, even if we set our time scale to something very long to acquire spectral data or spectral content over a long period of time. Now, under the settings, under time and frequency for the DPX display, when we have a DPXogram turned on, we can see a couple of parameters here. The time per division, in this case 5 seconds per division, is the same that I'm showing up here on the adjacent to the display. Tells me the time between the tick marks. The time resolution is telling me how much time I have between each trace, each row of pixels, or each spectrum trace that's entered into the ogram. Again, remember that's composed of a positive peak of all the spectrums that occurred within that last 100 millisecond time period. The display down at the bottom tells us what our total capacity is. So in this particular case, at 5 seconds per division at 100 millisecond resolution, I've got 1 hour and 40 minutes of time capture capability within the 60,000 spectrum traces that the ogram can hold. You can increase that time per division value to a very large value and have this thing monitor for days over time. Again, seamlessly, because each DPXogram trace is a max hold of all the spectrums that are occurring. If you need finer resolution, just go down to a smaller time per division. We'll get less resolution within, or less time gap, if you will, between each of the spectrum traces. Of course, each spectrum trace is composed of all of the spectral content that occurred within that time resolution since the last entry into the ogram. Once you've recorded all of this data, you can save this off very easily. If you go under File and Save As, and tell it to save a TIQ file, right here. And let's just call this DPXogram save. And hit save. It's just giving me a warning that this is only useful for a single channel, which is fine. I'll hit OK. And I'll select DPX spectra and all in history. So that will save all the DPX spectra that have already been collected into the ogram, and I'll hit save. Now that data is saved off. You can recall that later on and play it back. The way to play back the ogram data is if we go under the View menu and select the Replay toolbar that shows up down here at the bottom. And when we replay data with a real-time spectrum analyzer, we can choose to replay acquisition data, but in this case we want to replay the DPX spectra. And what that allows us to do is, in addition to just looking at spectral content using the marker here, we can scroll through all this history automatically. So I've got this set of VCR-like controls down at the bottom here, and if I say replay all, it's just going to scroll and play through all of that DPX spectral content. So you can look for things that are going on, you can set up masks to look for interesting events and that type of a thing. You'll also notice if I stop this that every one of these spectrum entries in the ogram is time-stamped. The timestamp is indicated here with date and time of when it occurred. So the DPXogram can be used to capture long-term spectral activities in a very space and memory efficient way by only storing spectral content and not storing the underlying seamless baseband IQ data, but also having it time-stamped and also having it effectively gapless by taking advantage of the fast DPX spectrum processing and building traces from that continuous DPX spectrum monitoring. I hope you found this video useful to understand how to use a real-time spectrum analyzer to do long-term seamless or gapless spectrum processing in your RF environment.